Welcome back to this first lecture about chemical process design. The aim of this part of Lecture 1 is to familiarise you with the piping and instrumentation diagram, or P&ID, which is the most detailed drawing produced by the chemical engineer. In essence, anything that gets built on a chemical plant is shown on the P&ID, no matter how small the item is or how infrequently the item is used. The next part of this lecture will introduce you to a workflow that will enable you to turn a unit operation on a PFD into a P&ID. We'll start this part of Lecture 1, however, by examining the level of detail that unit operations are illustrated with on a P&ID. We'll see that every last instrument, pipe and valve that connects to a vessel has to be shown. We'll also talk through symbolic abbreviations for pumps and valve assemblies, discuss piping codes, and introduce annotation schemes that are used. So when we think about a piping and instrumentation diagram, it is the most important process document as it links all the different engineering disciplines together. The piping and instrumentation diagram will be used as much by instrumentation and control engineers as it will by chemical engineers. There's also a significant amount of mechanical information shown as well, and so it becomes a starting point, or one of the starting points, for the mechanical engineering discipline to do their work. So when we consider how we communicate that information, we need to make sure that it is understandable by all. So therefore, P&IDs, as with PFDs, are drawn to a given standard, and also the revision numbers are very, very clearly marked on them, such that when these documents are used in a group situation, everybody is referring to the same version of the document. So in order to draw a P&ID, we have to have completed our process design. We also have to have completed our control design, because every single last piece of equipment is shown. Every single pipe is shown, every single valve is shown. The valves are also designated to be normally open or normally closed, depending whether they're blacked out or shown in outline. We also include all vents and all drains. We also include all instrumentation and every control loop. Paramount importance, we include every single safety device, every trip, every alarm, every relief valve, every bursting disc. We also give information around materials of construction of vessels and materials of construction of pipes, along with things like piping insulation or piping trace heating. Because we show every single last item of equipment, any piece of equipment that's duplicated is shown. For example, when we talk about pumps, we'll recognise that a single pump on a process flow diagram often corresponds to 2 or 3 pumps on a piping and instrumentation diagram. Now, because of the nature of the diagram, because it is such a key communication tool, we have to make sure that a strict standard is adhered to, and I'll be giving you more details about these standards as we go along, and in your note set there'll be some examples that you can use in order to draw your own diagrams. We also have a departmental P&ID standard to which all the P&IDs that are produced by you should conform to. This is to emulate what happens in industry, where a given company will have their given in-house style and in-house specifications to designate what should and shouldn't be shown on these drawings. The best way to talk about what's on a P&ID is to actually look at a P&ID and learn how to read it. So here on the whiteboard is a very simple P&ID, and so much as we did with the process flow diagram, we're going to take it apart piece by piece and look at what information is shown and how we can learn to read these very important pieces of information. So let's start by having a look at the vessel here. We've got a reactor of some sort, a packed bed reactor, R-1-100. Let's zoom in on that and see what information we've included now on this vessel. You'll note that it looks immediately more complicated than it does on the process flow diagram. There's a lot more information shown. So let's talk through these bits of information. The first thing that we have to ensure is that any unit operation shown on a P&ID is easily referenceable back to the PFD. So the tag numbers are the same. When we come to line numbers, they'll all be different because there are so many more lines on a P&ID compared to a PFD, but all our vessel tags are the same. So if we look to the PFD at R-100, we should be able to look at the P&ID for vessel R-1-100 and see the same vessel connected in the same way. So you'll see that there are many connections into and out of this vessel illustrated. There may only be one process flow inlet or one process flow outlet, maybe those 200mm pipes that are shown, coming in on the top left and the bottom right. However, there's more than that just connecting to a vessel. So think about instrumentation for a start. If we've got pressure measurement devices or temperature measurement devices, these instruments actually need to make physical contact with the fluid inside the vessel. And so a pressure measuring device typically will have some sort of strain gauge element that needs to be exposed to whatever gas is inside the vessel. Likewise, a temperature measuring device needs to actually stick into the vessel somehow, such that you've got an accurate measurement of what's inside the vessel, not what's happening inside the vessel wall. So if we're going to connect additional items of equipment into a vessel, it needs to be done so through a flange. So this is a bolted union in which you will get your instrument, you'll bolt it to a pipe stub, and that pipe stub will be welded to the vessel. Those two parallel lines that I've illustrated on each of the instruments represent the presence of a flange. And if those two parallel lines are missing, it will imply that the entire section is welded. And if you've got an instrument that you need to remove when it fails, you don't want it welded into the vessel. Welding of an instrument in many cases will ruin it anyway. And so we have these 40mm pipe stubs with flanges, and on each of those 40mm flanges we have a pressure sensor, then we have a temperature sensor, then we have another temperature sensor below the packed bed, and then we have a level sensor. Instruments aren't the only thing that connect into a vessel either. So if we look at the base of the vessel, we've got two blacked out valves, so they're designated normally closed. One's a 200mm line, one's an 80mm line. Now these will be vessel drains of some sort. So if we think about the unsteady state, if we think about wanting to inspect a vessel, if we imagine that there is a liquid surface passing through this vessel, we want to make sure that there isn't any liquid left in the vessel when people enter it. And so we have to drain that liquid down. And in order to do so, we need sufficiently large enough pipes to do that draining in a sensible time, hence the 200mm pipe. So if we're draining liquid, we need to think how the liquid drains. As a thought experiment, if you get a bottle of water that's full of water and turn it upside down, not a lot tends to happen. It tends to glug a little bit and it doesn't drain very well. That's because there's no means for vapour to displace liquid. And the same goes with a big piece of process vessel. If we haven't got a means for vapour to displace liquid, the vessel won't drain down. And so if you look at the top right hand corner, we have another normally closed valve with an 80mm flat pipe stub going to a flange, which is your vessel vent. So if there's a non-flammable, very important, non-flammable service inside this vessel, you can open that vent to atmosphere. That will allow air into the vessel, which will allow liquid to drain out of the vessel. If, however, there is a flammable service in that vessel, introducing air will create an explosive atmosphere, and so that needs to be avoided at all costs. And so what you would typically do is backfill with nitrogen, which in turn presents its own hazard, because once that nitrogen has removed the flammability hazard, it introduces an asphyxiation hazard for anybody who might enter. And so that leads us to these two personnel accesses, these two human access routes. There's two, because if this vessel is backfilled with nitrogen, we're going to put a fan at one, blow through air to displace the nitrogen once all the flammable surface has been removed. Note that the 750 on each of these manways refers to the diameter. That gives you an idea of the size of hatch that you might have to crawl through if you ever do a vessel inspection. We've already talked through how instruments are connected into a vessel by means of a bolted flange, but this is just to serve as a reminder that all instrumentation is shown on this vessel as well. And so we've got those two temperature monitoring instruments, we've got a pressure monitoring, we've got level monitoring. The final thing I'd like to draw your attention to is this pressure relief valve on the top left of the vessel. Again, it is bolted onto a flange, and your pressure relief valve is a key piece of safety equipment. If the pressure inside the vessel exceeds a certain threshold, this valve will lift, getting rid of any excess pressure build-up, which could prevent catastrophic vessel fracture in case of overpressure. We've also included here the pressure at which this relief valve lifts, 2.3 bar. So there's a lot of information here, and the take-home message is that everything appears on the vessel, appears on the P&ID. Let's zoom back out. Let's have a look at how material leaves this vessel. We've got a control valve and we've got a pump. And each of these items is illustrated by one symbol. However, we've already said that for pumps, you never find a single pump in isolation. And so it's very important now to realise how assemblies are depicted on a P&ID. Your P&ID has to show every single last item of equipment, but that doesn't mean to say that we can't do so in a way that is clear. If you look at the bottom red box, I've highlighted two small drawings, and the purpose of these will become apparent in a second. So let's consider pumps. If you've got a pump removing liquid from a vessel and it fails, you don't want to shut your process down. Pumps are mechanical items of equipment. They're subject to wear. Their efficiency can go down as they wear. They're also typically motor driven, and the brushes on motors can also wear and may need replacing. And so you never have a single pump in isolation. You have a pump that is doing the service, and then standby pumps that are ready to automatically turn on if another pump fails. And so typically you'll have one pump running and maybe one or two pumps on standby. Every shift the running pump will be changed, because you don't want to assume that your standby pump will work automatically. You want to test it. And so every shift you swap over the operational pump either to the second or the third in the series, depending as whether there are 2 or 3 pumps in parallel. So what you actually have is a pump assembly that I've shown in this diagram here. You have your running pump, might be the A pump, you have your standby pump, which might be the B pump. Now let's talk through how this assembly is constructed. The standby pump, the B pump, is shown isolated in normal use, and so we've got normally closed valves here on entry and exit. Both running and standby pumps need to be able to start up properly. Now, centrifugal pumps don't start if they're full of air. If we've drained the system down for maintenance and just reassembled it and we start the pump up, it's just going to be spinning in a gas, spinning in air, and it's not going to suck anything. So what we need to be able to do is to ensure that we remove any gas from these pumps, and if we do that, it needs to go somewhere, and so each of these pumps has a vent, so we can prevent these pumps from becoming vapor locked. We might force liquid through these lines using another means. We'll blow the air out of these vents, close the valves as soon as there's liquid present, and then once that pump is primed, it can start to run and do its job. Now, if we've got one pump that's running and one pump on standby, what we don't want to end up happening is for liquid being pumped by the running pump to backflow through the standby pump. And so we also have non-return valves on the exit of both running and standby pumps. Now, if we're thinking about taking a pump out of service for maintenance, we need to make sure it's safe to do so. So we need to make sure that all liquid has been drained out of the pump, and that's why I've illustrated drains on these pumps as well. Remember that we can't drain a liquid out unless we've got a gas to displace it. So if we're going to drain one of these pumps down, of course we're also going to be using the vents as well. So the vent here now serves a double purpose, both bleeding the vapour out of the pump on startup, but also allowing drainage to occur as and when we need it. Let's think about control valves. Control valves are also potentially large pieces of mechanical equipment. They're subject to wear. If your control system is well tuned, they shouldn't be moving a great deal during the steady state. However, not every single control system on a plant will be well tuned. I've seen control systems where the valve is constantly hunting around from one position to another, and so the actuator is constantly moving, the diaphragms are constantly moving, which means there is constant wear on all of these mechanical items. This wear accumulates, and after a certain period of time, the control valve simply either fails or ceases to control in the way that it's been designed to. Now, you don't want to shut your plant down because of a control valve failure. So what we do is we have a control valve assembly with a designed-in resilience such that if we need to remove the control element, we still have a means of keeping the plant operational. So the assembly that I've put on the whiteboard here is an illustration of how this might be done. Let's talk through this in a similar way that we talked through the pump assembly. First of all, we have the means to isolate the control valve if we ever need to. In normal operation, these valves are normally open, hence they're shown in outline here. If we do end up removing our control valve, we need to make sure that that resilience is there. So how do we ensure that the material still flows through this loop, even though it is subject to control? So we have a bypass loop, which I've highlighted. That bypass is normally closed, hence the black tin valve there. And note that there's also an orifice plate on this bypass. This can exist for a number of reasons. It could be to match the pressure drop in the bypass loop to the pressure drop through the valve assembly, or it could be just to throttle back the liquid that flows through here, or the gas that flows through here, such that the plant is operating with a degree of what's known as turn down during this maintenance procedure. If we're removing the control valve, as before, we need to make sure it's safe to do so. Imagine that you're the operator or technician removing this valve. You don't want to be put in a dangerous position. So you as the designer need to ensure that this operation can be done safely, that all the liquids that are present can be drained out, that if there's any toxic vapour, they can be got rid of. I've shown these venting to atmosphere, but they may well be connected into vent headers. More about vent headers in the next section of this lecture. And of course, if we're draining liquid, we need to make sure that it will drain. Hence, we need a vent anyway to allow vapour to displace liquid. We may elect to displace with air. We may elect to displace with nitrogen if there's a specific flammability hazard, or if there's a toxic hazard that we need to flush through. So we need to think very carefully what service this valve is operating with, what the safety considerations are, and how we design the maintenance operation to be as inherently safe as possible. Note on the bypass leg, I've also included a vent and a drain. Now, the way these have been included is incomplete because I can't uniquely drain this bypass leg without affecting the process flow, and so I probably have another isolation valve upstream of this assembly in order to do that. Basically, you don't want fluid just sitting in a bypass leg. If it's a corrosive fluid, over time it will just simply eat away at the valve seats, it will eat away at the pipe walls, and potentially, if that bypass leg isn't used for a decade, you could have had a decade's worth of corrosion happen before it's put into use. It's suddenly put into use, pressurised, and the whole thing fails. And so you want to make sure that the bypass equipment is in good, safe condition for use, and it doesn't exist sitting with a liquid in there for sometimes months or even years at an end. Now, we've talked about pump assemblies and control valve assemblies. We've talked about the need for a piping and instrumentation diagram to show every single last piece of equipment, but also the importance of clarity. And so we can resolve these seemingly conflicting issues by using symbolic abbreviations. On the P&ID proper, I have a pump with an asterisk by it and a control valve with an asterisk by it. These asterisks mean that you have a symbolic abbreviation. In the footnotes, which was that lower red box, you have a diagram showing what that abbreviation refers to. And so the pump with an asterisk represents a pump set with one running and one standby pump with the configuration shown. And the control valve with an asterisk represents a motorised control valve with a bypass loop, isolation and vents and drains as shown. And so rather than put each assembly into the P&ID every time, which would make it unreadably cluttered, you have these symbols which allow accurate but clear conveyance of information. Let's zoom back out and look at the P&ID once again. I've highlighted three things. They're all effectively containing similar information. I have an entry or an exit flag, and I have a piping code. Let's examine what each of these things actually has in terms of information. Let's start with piping codes. The piping code here on this diagram is a piece of text below the pipe, 80-NIT-1003-304. This code is to a given standard. The standard is in the P&ID standard that you can download off Moodle. There's no set universal standard, but what you commonly find is information pertaining to the nominal diameter of the pipe, the fluid that's in the pipe, a unique line number, the material the pipe's made of, and then optionally whether any insulation or trace heating is required for the pipe. So let's go through this item by item. When you're designing pipework, you must remember that you're not going to get a fabricator to fabricate a bespoke piece of piping for you. You're going to be buying it off the shelf in certain standard diameters. These are called nominal diameters. I've put a table of nominal piping diameters in your notes for reference. The next item of information is the fluid code. Again, there are many different ways of doing this. On the CEB P&ID standard, I've put a list of fluid codes that you should use for your P&IDs. NIT, in this case, refers to nitrogen. The number 1003 is now a unique line number. Note that there are many more lines shown on a P&ID compared to a PFD, so this won't be the same number that appears on the PFD, but it should nonetheless be unique, such that if different engineering disciplines want to look at line 1003, they're all looking at the same line. The final code that's on this piping code is 304. This is a material code. It designates what the pipe is made of. Again, there's a list in the CEB P&ID standard, but 304 in this case corresponds to 304 stainless steel. It's a very expensive material. You certainly won't be making all your pipe work out of 304 stainless, and there'll be a very good solid engineering reason why 304 has been specified for this particular line. There's one final code that optionally you can include on a piping code, which pertains to insulation. If you've got very hot or very cold material in the pipe, you don't want heat to be either lost or gained. And so it's common to lag pipes with glass fibre, for example, or even to include heating elements if you want to keep that surface hot. And these heating elements we call trace heating, and they can be electrical or they can be steam based. Again, there's a list in your CEB P&ID standard. When we think about P&IDs, we have to think that for a plant there can be hundreds of P&IDs. A complex piece of plant will have many P&IDs. So what we want to do if we're following a material flow from one P&ID across 5 or 6 different P&IDs is to be able to locate where that material flow leaves a P&ID, where it appears on the next P&ID, and so on and so forth. And so you'll note that what we have here is a grid referencing system. The last piece of information on this flag is H8. And so this gives the location and the P&ID number where we can find where this stream came from. So this stream originated on P&ID number 103, and it was in cell H8 on that P&ID. Now, typically we're only going to be showing process flows on the P&ID, not utility flows as well. We typically have different sets of diagrammatic information, utility flow diagrams, that show flows of cooling water, of steam, and so on and so forth. If we included all the utility flows on a P&ID, they would get very hard to read and very cluttered. Okay, let's zoom back out again, and let's have a look at a very simple example of a control system. So there's a control system here which controls the level in the base of R1-100, and it does so through a control valve. So let's see how that's constructed. Now, control schemes are going to be used by the control engineers in order to design the electrical and pneumatic equipment required to suitably control your plant. And so you as a chemical engineer need to make sure that you are drawing these control schemes to a standard that is understandable by other disciplines. So ISA 5.1 1984 revision 1992 is a standard that we use. And I've put some examples from this standard in your notes so that you too can use these symbol sets. Now, the basic idea, and we're going to elaborate far more on this in the next part of this lecture, is that if you're controlling something, you first of all need to measure something, you need to translate that measurement into a signal, and then that signal needs to go somewhere that does something, either in terms of displaying, or moving an actuator, or sounding an alarm, or data logging. So, what we're displaying on this particular diagram is that we've got the base of R100, an instrument that is taking a level. So LRC is a level recorder controller, and so that control element is sending an electrical signal, which is the dashed line, through to a motorized control valve, which will know how much to open or how much to close according to the set point level. We're going to talk a lot more about how we think about this in the next part of this lecture. Also coming into that motorized control valve is an electrical signal from a diamond which says ES. That diamond with ES in is emergency shutdown. So this particular valve may need to either fail open, fail closed, or stay where it is during an emergency shutdown situation, and hence the signal coming in from ES, the emergency shutdown system, would override any of the normal control systems. Let's zoom back out and we'll see there's a big pane of text on the right hand side. Let's briefly look at the information that we've got there. This pane of text is in effect a commentary and a description. We want to assist the reader of the P&ID with their understanding of the process that we've designed. So first of all, we're going to give a very short description of each of the function of the control loops. It doesn't have to be an essay, but it has to be enough information to understand what's being measured, what signals are being used, what it's controlling, and if there's any underlying control philosophy, how this control loop links into that control philosophy. We want to give safety information. Trips and alarm systems are going to be segregated from control systems, because if we have a control system fail, we don't want our safety system to fail. And so we need to detail what emergency trips and alarms we have. Then we need to detail what happens in an emergency. What shuts down, which valves open, which valve closes, which valves stay the same. Finally, we want to make sure that if there's any other additional pieces of useful information, that they get captured too. And so we've got this section of general information that may include, for example, information about double isolation, information about safe vessel entry, and so on and so forth. Right, let's have one final look at our P&ID, and I've highlighted the border and the information box. Now, much in the same way as a process flow diagram, we need to be able to easily reference where things are on the diagram. Remember that typically for a big plant you might have hundreds of these, and they might be on A0, and if you're trying to find a certain instrument on a certain page, it can be very helpful to have a grid reference with which to locate it. Because of the importance of these documents, we need to know certain pieces of information about the document that we're looking at. We need to know who drew it and when it was drawn and so on and so forth. But most importantly of all, we need to know what process it refers to and what revision number it is. The importance of version control cannot be overstated for the purposes of clear, accurate communication. So please make sure whenever you're drawing a P&ID that you always update its revision, and that if you're communicating with others via a P&ID, that you're very clear about which revision P&ID you are working from. So let's recap a few key points. The piping and instrumentation diagram is the most detailed drawing that the chemical engineer produces. It contains every single item that appears physically on the plant, no matter how small it is or how infrequently it is used. Clarity, therefore, is essential. A badly drawn P&ID can be incomprehensible. And because it's such an important communication document, you need to have comprehensible, clear information. We can assist clarity by using symbolic abbreviations for commonplace assemblies, for example, valve assemblies, pump set assemblies, instrumentation assemblies, and so on. Every line has a unique code that gives not only the nominal diameter of that line, but also its unique line number, the piping material, what's in the pipe, and some idea about insulation. We've also got the P&ID drawing page as containing a grid referencing system, which is very important, and also essential to version control, information about who drew the diagram, when it was drawn, and what version number it is.